Okay, thanks a lot for inviting me, and I understand that I have to stay in time, so I have 30 minutes, or should I be faster? Then please indicate if I am running out of time. So
Yeah, Sally, yeah, you have, if you can like finish in 25 minutes, that would be nice.
I will do my best.
Yeah, thank you.
Just as a motivation, so this talk is about how to determine size of networks, and it's actually I have to thank Igor Mesic for his nice talk, and the last slides, which will be a nice connection to my talk. As a kind of introduction, so you see the famous image of Michel Foucault. Ceci n'est pas une pipe means this is not a pipe. And why is this not a pipe? Because it's a painting of a pipe. And indeed, it's not even a painting of the pipe. What you see is the image I took of a painting of a pipe and now transmit through internet to you. So you see an image. And now the question is, what does it mean and how can I train artificial intelligence to recognize images? So it means we have sensors, we have interpretations, and what is reality? This is something philosophical, and we will not comment on that. But what we need from reality is a joint concept on things, for instance, of a pipe. So we can either let our intelligence learn it unsupervised, or we supervise things, and like we teach children and say, this is a pipe, then the child says pipe, and so on. What do we have in as sensors? We have some neurons in our visual cortex, and the information is stored in the brain. Artificial intelligence is thought to mimic that. So let us consider neural networks as statistical systems. Since we have so many sensorical information, I want to dwell a little bit on that and hope that it will become clear why. So there are many approaches and analogous to statistical mechanics of the brain. So people formulate kind of Hamiltonians, say we have neurons and we have connections between the neurons as axons. And then these neurons are now called S. We have Si and Sj, and somehow they are coupled through coupling matrix Jij. Of course, there are other formulations. That's a kind of simple thing which fits well to our statistical mechanics understanding. Me being a physicist, I try to somehow transfer what I know to machine learning. So this system is driven by a external force h of t, small h of t, and we sum up the individual neurons. So what we measure in quantities, in terms of statistics are mean values most of the time. For instance, we can call it magnetization, and there I already interpret this model no longer as neurons or axons. I say it's a kind of synchronized action or alignment of my neurons such that I have an extensive quantity, and the better they are aligned, these different neurons, the larger the so-called magnetization. So what's the connection to neural networks? Let us consider deep neural networks in a special setup. So if I have an input X, and my network is described by weights and nonlinear functions sigma, so they are typically sigmoid functions, and I have P layers of my network. Then I have a concatenation. So I have in a kind of concatenation these. I execute my nonlinear functions on the input value, and I execute it again with different weights on the result, and so on, until eventually I arrive at a result Y. So Y depends on how the weights are set, and it depends on my input values X. So let me draw here kind of analogy already to the driving. So if I consider a time-dependent driving of my neurons, then I could say I present a series of pictures very quickly to my neural network, and that is kind of driving my network, and the response is, because it has a memory, the response is how the network aligns to my external driving. And we say in a supervised learning setting that we want to minimize the empirical loss. So in that case, we formulate the loss as the average over the individual capability to recognize correctly my input. So, and in the simple setting, of course, this is all models, we say my classification is correct. Fi is 1, is 0 if it's correct, and it's 1 if it's incorrect. I choose it in that way because I want to have a minimization problem. So I have my objective function, f of w is a non-convex, sorry for the misprint, is a non-convex function of w, and the optimization problem consists in finding the set of weights such that the my objective is minimized. So when we have a measured quantity, so we can say this is a kind of thermodynamical quantity, since it's again a mean value, for instance, of the absolute value of my objective. So here I made it a bit more concrete because typically it's not as easy as having only zeros and ones. We may have many different classifications, many different classes. So that's a kind of generalization already. So let me summarize this analogy. We have weights and coupling, we have classification and from physics, magnetization or recognition in our brain. And the objective corresponds to Hamiltonian. All this is known, but I want to repeat it and present it in that way such that we can come to easier to understand my approach, how to analyze the system in a minute. So we want to find the ground state in of the system or the optimal solution. So that means, but that is typically very expensive since the number of macro states is huge. So we typically accept solutions, we run epochs, we run over epochs, we have an iterative procedure to find optimal weights and so on. So we typically accept approximate solutions. So we as well describe our quantities by mean values. Mean values are sharp in the statistical mechanical sense. So stat-mech, pardon me, the abbreviation, is to describe the statistical mechanics. So there we have huge numbers, not 10 to the 9, we have 10 to the 23, and there we have sharp mean values because we have such a large number of variables that averaging means we go from, say, if we have a Gaussian, it gets more and more delta-like. And the parameters, they are equivalent to constraints. So if we have something that constrains my system, then this is called in the conventional language parameters. We can solve these problems with constraints by, for instance, Lagrange formalism or numerically. So all the machine learning algorithms have clever algorithmics and clever numerics behind. So I will not talk about how to solve how to obtain the weights, but I just want to mention that typically if you have very large numbers, then we have a formalism which is Lagrange, so we can formulate entropy, and based on the entropy we have a free energy, and we can as well formulate additional constraints and define our setup in terms of canonical, microcanonical, or grand canonical ensembles. Important here is this small wi. The wi is typically the volume of state space that is occupied by a state, and we have an exact expression for it. And based on that expression, we can do computation. So for instance, let us sidestep once more. This Ising model here means that we have an exchange of energy between Si and Sj, and we have an external driving which aligns my spins. Intrinsically, it might be favorable that all these S and Si and Sj point in the same direction, or they don't. Certainly, if I have a very huge driving, very large driving, they will align. So what happens is that here, hidden in this formalism, is that I have E equals T times S. It's a thermodynamic relation, and there is temperature involved. So mean energy or temperature determines the transition from magnetized to unmagnetized system, which means all of these variables are 1, or all of them are 0, or they are completely random. So if I have a large driving force, I align my variables. If I have only stochastics, I don't. So that in typical terminology of phase transitions, we say we have a temperature, we have a magnetization, and this magnetization goes to 0. At the critical point, it stays 0 because the temperature is too large, such that the energy which is intrinsic or with driving is not large enough to align my state variables. And just as one example, which shows as well kind of typical behavior, we have a divergence of correlation function to at the critical temperature. The correlation function gets as in terms of the mean values, you see, then this gets as well very large. So it diverges. Let us see if we can do for our neural networks. What is temperature or the noise in the deep neural networks? And there I can come back to the talk of Igor Mesic, where he said as well, okay, we have digits, we have resolution in our images, and we might have as well accuracy in our data. So depending on the noise, which I have only a very vague definition for the moment, we can say, okay, if there's high noise, there's no recognition. For instance, if I have only pixels, I will show an example in a second. I can recognize or classify something. If not, if I have no noise at all, it will be very good. If I have high noise, it will be impossible. So as a working definition, I say noise is anything that does not belong, sorry again for the misprint, to the object to be classified. Wrong pixels, objects covering a face, insufficient resolution, or maybe just a very bad setup, accuracy of my numbers is not large enough, things like that. You can as well imagine now coming to an application. Why is that important? You have an autonomous car driving in winter and it starts snowing. This car should recognize where it drives on a road. And this is a real example and it's really applied, and we are working on these problems pretty urgently. So let us assume we have a camera, starts snowing, then step by step, if it snows more and more and more, the camera will recognize less and less and less about the surrounding. And if the car is programmed correctly and the artificial intelligence responds correctly, it will stop when it stops classifying its environment as a road. Yeah, so this is a very important example, and there are many others. You can fancy that. So with increasing noise, the transition from successful classification to impossible classification happens. This depends, of course, on the complexity of the problem, on the size of the network, on the number of iterations of the learning time. If we have trained our artificial intelligence badly and it doesn't know what a road is, then it should stop immediately, of course. So asymptotically, we, of course, can assume something. So what would be ideal? We can say infinite training time, infinite number of nodes in our in the deep learning network. and we have an infinite number of images. All images that are possible are fed to my infinite network, and it can learn infinitely long. This is kind of unrealistic, of course. So let us
Markus, Markus, do you hear me? You have 5 minutes left, yeah?
Yeah, I know. So
Yeah, okay.
I come to the point in a second. So what I want to do is image recognition. So the number of weights is not too high. So we have 10 to the 12, and we investigate noise dependence. So I explained what I expect. So I skip some things. I want to see if I can find a transition from classification to non-classification. So we know that there is a kind of finite size scaling, so that will give us how many data are needed to find a classification. And eventually we want to understand if we can recommend the optimal model for a given problem. So let us add noise to numbers. You see from left to right, it's getting worse. Yeah, so we do exactly this experiment, we repeat it many times, and apart from the interpretation, I skipped that. We use the same data we saw before in the Igor Mesich's talk, or at least he did one of his many experiments on using these data, as far as I understood. We have a few instances, few thousand, and take the number set from MNIST. So apart from the problem from these data, what we observe is the following. We increase noise from left to right. So I will only show the most important picture. So you see clearly a transition from classification successful to classification unsuccessful for a certain noise level. So we did that for many different data in order to see if we have a finite size effect for the data feeding. And of course, we did it as well for different sizes of our network, which I don't show here. It is basically equivalent. So the question we have now here, we know from phase transitions, and this is something important, is there kind of universal behavior? So let us plot. Oh, I didn't explain that. So sorry, you made me panic a little bit. So we have here in this curve, we can determine the width of the transition. And the width of the transition depends on the number of images we feed. And if we now plot, look, always on a logarithmic scale, the number of images and the width of the transition, this is over 1 decade, gives us an exponent of 1/2. And I know that this is clearly a cheat for everybody who is familiar with scaling. We have to increase that, and we are now repeating the whole thing with a transformer network and analyzing tweets, millions of tweets, so we can do all this much more accurate. But the main question is for us, is there any universal behavior? And this has been asked or even answered by Igor Mesic too. He has a spectrum of his Koopman, of the Koopman operator. And having the same spectrum, do we have the same system? I would not say that, but what I say is maybe there's universal behavior, and I don't care if it's exactly the same system, but we can say, if we have universal behavior and know how my system scales with the number of images or how many nodes I need in my neural network, can I determine the amount of data to reach a certain quality of the classification? And the quality is given, of course, by the sharpness of the transition and at the temperature point, at the noise level. So some networks might be better or not, given a certain noise level. Faster recognition, smaller networks, all these things might be hidden in a kind of statistical properties of the architectures. And we can as well turn the question around and say, knowing the amount of data, what minimum size of the network do we need to reach a certain quality of the classification? And this is, I would like to emphasize that point because I encountered many people, we have many data now from climate things, and there are images, and some people start doing analysis, they use huge networks for a few thousand images. And this is, of course, maybe not, given the complexity of the question, maybe not the right way to analyze these things. Skip these things. So I think, as a summary, analogy can be established. We can, of course, for small networks, we need corrections. For large networks, we may use all this statistical mechanics, in particular phase transitions. I want to find if there is a universality in certain model classes, which amounts to kind of computing spectrum of models. And we want to see how much the models and the results and classifications depend on the driving. That means the statistical properties of the data. We want to see how the size of the network depends maybe on this scaling. And eventually, of course, we know that if the task is complex, we need more and more, bigger and bigger networks. And maybe one can find kind of asymptotic behavior and use that to a priori set kind of the size of the networks. So that is basically what I discussed. So I wrote it here as the outlook. What we will do next is study really different architectures and try to classify them according to their scaling properties at a kind of classification transition. And of course, the more complex question will be unsupervised learning, where we have feedback loops and everything will get even more complex. So I'm sorry, I hope I made it in time and finish and say thank you to the audience for listening. I hope it was interesting.